So today I am going to talk about space-time symmetry. Here today in this lecture I will talk about the introduction of this. So symmetry or invariance play a very important role role in physics. There are two broad categories of symmetries in physics. There are two broad categories of symmetry in physics. Let me talk about those. So categories of symmetry. So there are two categories. So first of all, it is the space-time symmetry. And another one is internal symmetries. So let me write down it as not symmetry but symmetries. And internal symmetries. So let us talk about their examples. So first of all, let me talk about space invariance. And this leads to conservation of momentum. This leads to conservation of momentum. Another example is spatial rotation. And this leads to law of conservation of angular momentum. This leads to law of conservation of angular momentum. Another one is translation in time. So space invariance is also related to translation in space. This is related to rotational translation, and this is the translation in time, and this leads to energy conservation. This leads to energy conservation. And here are a few other examples of the internal symmetries. So let me first of all talk about rotation in isospin space. And this leads to isospin conservation. And another is spatial inversion. and this leads to parity conservation. This leads to parity conservation and particle antiparticle conjugation, particle antiparticle conjugation, and this leads to C parity, leads to C parity. And another one is gauge transformation. And this leads to charge conservation. Charge conservation. Charge conservation, right? So this is all about all these things. So it's a brief idea of the symmetry. So let us now talk about the categories. Let us now discuss what is invariance principle. So let us now discuss that what is invariance principle. Invariance principle. So if a system remain unchanged with the application of some transformation then is said to be invariant under that transformation. In quantum mechanics, such transformation is described by unitary transformation. So let us now talk about the types of transformation. So types of transformation. So first of all, first is the continuous transformation and another one is the discrete transformation. So continuous and discrete. So translation and rotational transformation are its example. Means here translation and rotation. Translation and rotation transformations are its examples. And here spatial reflection through origin is its example. And this leads to parity operation. This leads to parity operation. So let us understand. Say its axis, and here mirror is placed here, so a particle here, it seems to be here. So this is the spatial reflection through the origin, is its example, right? So in this lecture I will discuss translation and rotation transformations, or so let us start with the space translation transformation. Spatial translation transformation. Let me first of all talk about it, and after that I will talk about the rotational transformation. So the effect of an infinite simul translation delta r in space on a wave function psi is given as, means it will become a psi prime, means if r changes from r to delta r, right? So this can be written as psi r plus delta r curly psi r over curly r, and we can write down it as d psi. Here d is equal to 1 plus delta r curly over curly r. It can be written using this equation. So is an infinite simul space translation operator and let us recall momentum operator. So if we look at the momentum operator, that can be written like this, that P is equal to minus iota h cross curly over curly r. So that means this curly over curly are sitting with the momentum operator. So let us try to express this space translation operator in the form of a momentum. So for that we can write down using this. I can write down that curly over curly r is equal to P over minus iota h cross, and 1 over iota is minus iota, so this makes it iota P over h cross into delta r. It can be written like this, sorry, not delta r, yeah, it can be not this one, but its value can be written like this, and if I put its value from here to here, then this d will become, this d can be written like this, 1 plus delta r curly over curly r, and it can be written as 1 plus iota p over h r into delta r. But a finite translation delta r can be obtained by making n steps in succession, n steps in succession, and here n approaches to infinity. So for a finite translation, we can write down that d is equal to limit n approaches to infinity and 1 over iota p over h cross delta r over n. This is the value, because delta r into n gives you delta r. It can be written like this. So using this I can write down this one. And n steps means raised to power n. But if I recall 1 over x raised to power n, 1 plus x over n raised to power n whole raised to power n, it is e raised to power x. If I put and limit n approaches to infinity. So if I use this limit, then it can be written like this: e raised to power iota p over delta r over h cross. But in natural units, h cross is equal to 1, so therefore this d can be written as e raised to power iota p delta r. Another thing which we have to keep in mind, that if I try to find out d dagger d, then it is e minus iota p delta r e raised to power iota p delta r. This will cancel out with it, so it will be 1. So thus d is a unitary operator. Thus for space translation, from this discussion we concluded that thus for the space translation, momentum operator is the generator of this translation, this transformation. And unitary operator for this transformation is e raised to power iota p delta r. Thus, and this transformation leads to, and this was discussed in the course of quantum mechanics, so this transformation leads to conservation of momentum. So this is all about spatial transformation. Then let me talk about the rotational transformation. Next is the rotational transformation. So the effect of an infinitesimal rotation delta phi in space on a wave function psi can be written as psi prime is equal to psi phi plus delta phi, and it can be written as psi is a function of phi plus delta phi, and curly psi phi over curly phi, and it can be written as psi phi or psi phi. And here r is equal to 1 plus delta phi curly over curly phi is an infinite simul rotation generator. So let us now recall z component of angular momentum. Recall z component of angular momentum as this z component is just by convention. Also, angular momentum is related to rotation, as angular momentum is related to rotation. That's why I am considering z component of the angular momentum. So Jz, it can be written as minus iota h cross x curly over curly y minus y curly over curly x, and this is basically equivalent to curly over curly phi. So therefore this Jz, it can be written as minus iota h cross curly over curly phi, means Jz is equal to minus iota h cross curly over curly phi. So from here I can write down curly over curly phi as equal to Jz over minus iota h cross, and it can be written as Jz over h cross multiplied by iota. So therefore r can be written as 1 plus iota Jz over h cross and delta phi. So for finite rotation, delta phi is equal to n delta phi. It can be written as delta phi is equal to delta phi over n, where n approaches to infinity. Therefore this r can be written as n approaches to infinity, it's 1 plus iota Jz over n h cross, and here n steps have been taken for succession where n approaches to infinity. So keeping this in mind, we have to take its power n, and this can be expressed as e raised to power iota Jz over h cross into delta phi. And in natural units, we can write that r is equal to e raised to power iota Jz over h cross, Jz into delta phi. And here r dagger, it again comes out to be unity. So thus for rotation transformation, angular momentum is generator of rotation transformation. Also r is equal to e raised to power iota Jz delta phi is unitary operator. And for this transformation, angular momentum is conserved. So that's all for this lecture, and in the next lecture I will talk about the parity, right? So that's all.